huge cast of people, but there's a few in this room who I work with. There's Eckert and Natalie and Claudia and others I've worked with in the past. And then there's a whole lot of people who I do the Martian stuff with, and a lot of people in Switzerland I worked with on avalanches. So I'll try to look at the big challenges. The first one that I'm most interested in is what to do. How can we mitigate geohazards with a changing climate? This shows a picture from about 10 days ago for a hotel in Switzerland. Now, Switzerland, they the gold standard really for hazard zoning. They are very careful about where they let people build things, and they look at the historical record and they work on a 300-year cycle, so things should not get hit. Things like this should not happen, and it almost never does happen. It's extremely rare. In Italy, where they're a bit less strict about their hazard zoning, it's a bit more common, and this is a this is a hotel. This was a hotel that was destroyed. In America, they have no hazard zoning because if people have houses in places which are dangerous, if someone wants to hazard zone it and say this is dangerous, then they object. So there's lots of buildings which are built in places which will get destroyed every 50 or 100 years by avalanches or rock slides or other things. But the point is, in Switzerland, they really are very, very good at this. And in general, in France, they're very, very good at this as well. Even though in '99, when I worked in France, there was an accident just up the valley from here in Montroc, where the mayor had overruled Seamagraph, who made the hazard maps, and he allowed some ski chalets to be built, and they all got destroyed. And they were exactly in the red zone, on the edge of the red zone, from an avalanche from I think like 1913 or something. So that is how all that accurate hazard zoning is done, is on the historical record. And if we have to use our mathematical models, they're pretty rubbish compared to talking to old people or looking at where the trees, how old the trees are, which is generally the best method. If the trees are less than 100 years old somewhere, then they've probably been destroyed by something coming down, and that's much better. So the problem is that the models that we have are not good, and if the climate's changing, it's no longer stationary, we can't use the historical record to be sure about where is safe and where is not. And though probably in general as the climate warms, we will get fewer things like avalanches, we may get bigger ones if it starts warming earlier in the year when there's a bigger snowpack, for example. Another hazard that's changing a lot is rockfall. In all the mountains, the permafrost is melting, so we're getting massive rockfalls and destabilization. So you get the initial danger from the rockfall, which can be, completely destructive. Nothing will stand in their way. But then you have all of this debris that's been left by a rockfall, and the main thing that reduces the occurrence of debris flows is lack of supply of material. But if you have some massive landslide or rockfall, you suddenly have a huge amount of material that's not well consolidated. As soon as you get heavy rain, that's going to form a huge debris flow. There's going to be a big increase in all these type of events as the climate changes. Now the second thing, I do quite a lot of planetary science. Now if we fail to mitigate climate change, people often say we should escape to Mars or something. I think this is a crazy idea because Mars is extremely inhospitable. But I'm also going to talk about some of the hazards that one faces on Mars. This is from The Martian, trying to survive there. This was a graphic someone made about some of the work I did on Mars, which, depending on time, we'll get onto later. So there's all sorts of geohazards there. One of the interesting things about trying to apply the same sort of models on Earth and Mars is that they really ought to agree if the physics is right. The fact is a lot of them don't agree, and that's because the physics isn't right. Parameters have been fitted, they don't have the correct underlying physical processes, so if you change gravity and pressure and temperature, in theory everything should still work correctly. So it's a really great test if they don't. And Mars is interesting because there's no liquid water, despite the fact people have waved their hands for a long time and tried to explain a lot of the flows, which I'll get into. There isn't really any water that can mobilize these things. Now that's the sort of the big picture. The small picture is, in a sense, is looking at what are the actual equations. So this is what's known as the Bassett-Boussinesq-Oseen equation by some. So if you've got a particle mass m moving with speed v in a fluid, it's going to have gravity, it's going to have some drag. You get kind of complicated functions for this that you can choose however you like. You can get added mass effects. There's also some times you can get these things differently. So this is the fluid acceleration. This is the fluid velocity. Got fluid Kylov, just density gradient. Then you have the Bassett term. This is generally about as much as you ever see of the Bassett term. People will write it on the first slide and then ignore it because it's very difficult to incorporate. I'm not aware of any real work that's used this. There is a little bit on particle tracking, but it's much harder to put this into a continuum theory, and this is as much as I'm going to talk about it. You can also have some singularity. So it's very unclear, when do you need these terms? When are they important and when are they not? And some of the work I think Eckert will be talking about later is they're doing these direct numerical simulations now where you can actually start to say perhaps exactly what terms are important. So then the big question is, mostly if you're trying to get towards a simulation, even if we're talking about what we call DNS, we're not doing DNS in the sense of resolving the smallest scales generally around particles. We normally treat the particles as a continuum field, so reducing it in the same way as temperature or salt, and then you get this type of equation. And you always have a diffusion term in here for the particles. Now if it's salt or temperature, this is pretty straightforward. If it's particles, it's not straightforward at all where this D comes from. But you have to put it in there, and you generally make it the same as your fluid viscosity. So if you don't do this, then your numerics go wrong. And that's generally where it comes from. And there's some evidence that once you make it smaller, it doesn't have much effect. But you need it just to make your numerics work, even if what you're claiming is DNS. Then you might have a sedimentation velocity, and then there are ways of incorporating some of these other terms, like the added mass and inertial effects. So the question is, what is D? And then there's also a question of what is the effect on the turbulence. So this is a DNS of a plume that I've been doing some work with Claudia, that if you have particles in the plume, they actually have quite a difference. So this is the salinity. So this is actually lack of salinity, I should say. So it's fresh water rising in salt water, and this is the particles which are denser. So this happens where ice sheets go into the ocean. You get a plume coming up, and the experimental observation is that they dramatically affect the entrainment rate. So this alpha we were talking about yesterday can vary by almost a factor of 2 if you have a few percent of particles in the plume. And as far as we can tell so far, if you just have this part of the equation, you do not get that effect. The particles don't do anything special. They don't affect the entrainment. So the plume, so that shows that some of these other terms are necessary to get these things right, to get the effect on the turbulence, and they can have a dramatic effect on the melting. As this plume is rising up by the edge of the ice, they can dramatically affect the heat transfer. That can also then therefore vary by a factor of about 2. So the ice sheet can melt twice as fast as you might expect if you have a few percent of particles in there. So then it's a question of, what are the terms that lead to this back effect on the turbulence? What do you need to do to get this right? And hopefully at some point we'll know the answer. So far I know that it doesn't work if you don't include them. So there's all sorts of geophysical flows, and I'd say avalanches they're the easiest one to study because they happen reliably in the same place over and over again. You can trigger them. They melt, so they don't change the topography that much. So you have the same type of background each year, and they're less destructive. So generally speaking, you can put things in the way, take measurements, and they will survive. So that doesn't always happen. A lot of our radar system got destroyed last year by an avalanche, and every now and then the big avalanches will break things. But compared to pyroclastic flows or debris flows or rock slides, they're much easier to study. At the same time, the underlying structure of the models should be very similar. So the idea is not by studying something like avalanches, you're not just trying to figure out avalanches, but also turbidity currents, which will also be very similar. So these are currents that are under the ocean, which are much harder, again, to observe and destructive of undersea cables. Maybe they would affect undersea mining, oil platforms, and so on. But often what you have, you've got a dilute turbulent suspension cloud. You've got a dense flow, which is going to be more like a solid granular flow at the bottom. And then you have some kind of transition region, which is argued about a lot, and nobody quite knows what sort of, whether you have a sharp interface or whether you have something that's more well mixed. And again, this comes on to some of the issues that Colin was talking about yesterday. This is actually from a review article with Eckert, this figure. Now, this is a thermal camera of an avalanche. It's showing you the temperature of the snow, and this is nice because it shows you where the snow is getting entrained from, because the snow is at different temperature at different heights in the snowpack. The actual dissipation effect on the temperature is not that big, but what you can see here is that the powder cloud's completely separated away from the dense flow, because this very small avalanche, you can see extremely clearly where the deposit is. That one's just broken. This was actually the full experiment. So despite this being Switzerland, he broke the safety rules. You're not normally supposed to fly a helicopter with more than one lit stick of dynamite in at a time, but he lit all 6 so that they go off at the same time. Then he's flying along and throwing them out. So the pilot had a lot of trust in this guy, and you want to make sure one doesn't get stuck under the seat. But it does make for a dramatic effect. So this was the full thing. So this is what's nice, is that you can make them whenever you get time to use the helicopter. I think it's a bit expensive, but it's a lot cheaper than other things. So here you've got this dense flow starting of particles, and then because these slopes are so steep, they're very rapidly mixing with the air. And it's this transition process, again, which is still not understood. So this is the big challenge, really, to get the complete initiation and the mixing between these layers. And then you saw in the thermal camera the separation, and here you can see the dense flow underneath. The other interesting thing that you'll see in the dense flow is there's a whole series of surges or roll waves. And these have been studied a lot by people like Neil Bamforth, and you get them in just Newtonian fluids, but also non-Newtonian fluids. But if you get these instabilities with these waves developing, that means you get much larger heights and velocities inside than you'd expect if the flow is uniform. So you get much larger destructive forces. So if the flow is going to be twice as deep in one of these surges, it might be moving 4 times as fast. So that could make moving 4 times as fast, that would make the force 16 times bigger, but it's twice as high, so it could be 32 times the force just from having these roll waves than compared to having a straightforward uniform flow. But all of the models that are used at the moment have too much dissipation in and to get this transition right. And it's actually pretty tricky with roll waves, even with a Newtonian fluid, to do this correctly. So Manville had a series of papers where he did the correct long wavelength expansion to actually get this transition between uniform flow and roll waves. But none of the models that are used at the moment get this correct. Now, one way you can try to get this 2-layer structure, the simplest way perhaps, is you're going to change your particle flux. So this is where the diffusion comes from, is the particle pressure. And what you need if you want to get a dense layer is you need a more realistic particle pressure. So when you're studying granular flows, this is your kind of granular equation of state, and in front of this, to get the pressure, you'd actually have the particle diameter squared and the granular temperature. As far as these models are going, the important thing is that you get a kind of a divergence at the maximum packing fraction, so that gets your particles to stick down, so you can form these two-layer models. Of course, this can give you trouble with your numerics. You've got to be careful that phi doesn't get above phi c, so the problem becomes very stiff in this region. So what are the correct numerical schemes, whether you want to change your variables so that phi is going to go from 0 to infinity instead of 0 to 1. You can rescale things to prevent these type of problems, but how to solve these efficiently is an issue. So this, for example, this is in periodic boundary conditions just for simplicity. This shows you that when the particles resediment, as well, rather than the whole thing just mixing and disappearing, the current can continue for quite a long time. I'm going to skip through to the best one. So this is so it's mixing on the upper surface, the particles coming back down, and then maintaining this gravity current for a long period of time.
This is inclined?
Yeah, this is inclined. This is on a slope. And here we're not actually balancing gravity, so there's no drag, there's no net drag at all, so the whole thing's accelerating and then it becomes unstable. But we can start to look at the effects of sedimentation on the upper surface. So a big powder snow avalanche doesn't matter, it's just going to keep on in training, and the sedimentation velocity of the particles is very small. But turbidity currents can run for hundreds or perhaps even thousands of kilometers, and they seem to be very stable. And it's a question of that, there are some of the effects that Colin was talking about where the interfaces can stabilize, but this is also aided if the particles can sedimenting back down. So even if the interface is unstable and there's some mixing and diffusion, the particles can come back down, and that means that these flows can continue for much longer than you'd expect. So if we look at the debris flows, which are going to be much more of a hazard, I think, now that we're getting all these massive rockfalls, Ilgraben is a location in Switzerland, and what's unusual about this is due to plate tectonics, the whole range is basically under tension. So the rock is breaking up extremely rapidly. So I've walked up to the top of here, and it's really quite frightening because it's totally unstable. You come up to the top and there's just this drop, and every year there's meters and meters of material that are coming down. So there's this huge supply of debris, and that's an unusual situation. But if there's more rockfalls, that's going to become more common. So they get lots of debris flows there. Actually, let me go back. This is what one of them looks like from a few years ago. I think it's still the case that there's only 2 data sets where everything was working, and that shows you the difficulty of taking measurements of debris flows, because you get these huge boulders coming along, and this is a small one, and they're very destructive. And a couple of years ago most of the instrumentation was ripped out, and it's now being replaced. But what you're trying to measure are things like the pore pressure in the fluid, and the reason these things mobilize is that there's a large pore pressure, and that's supporting the rocks in some way. So you've got to figure out how are you going to solve these type of problems, and you're never going to. This is what it looks like. All of this got taken out. You've got something here that can measure the surface sensor. There were load cells here which would measure the particle pressure, the shear stress, the pore pressure, also some sensors at the side. And I think it's the best part of £500,000 francs to replace all of this. But what we'd like to be able to do is have a continuum, a shallow water model that will do it. And what you can see from one of these data sets, for example, is that the height under the bridge rises rapidly. The normal stress rises rapidly, whereas the fluid pore pressure rises much more slowly. So normally at the front of these things you have basically a dry granular flow. There's no fluid, and it's being pushed from the material behind. And then later on the pore pressure rises, and then the ratio of the shear force to the normal force, i.e. the effective friction, then drops, and that's what keeps the whole thing mobilizing. So it's how do you incorporate this into a shallow water model so you can enable the pore pressure to increase or decrease, and therefore affect the mobility of the flow. So if you just look at a normal zeroth order shallow water equation, so if it's just everything is continuous down the slope, then you're just going to have the acceleration, you've got gravity pulling it down, then you have some effective friction, and these effective friction laws, it's going to be proportional to the Froude number squared. It's like a viscous type of it's like a turbulent Chesy drag, or you could have a viscous thing, but really it should depend also on the solids concentration at the bottom and what the pore pressure is. So if the pore pressure is equivalent to the weight of solid material, then the thing is going to be behaving like a viscous fluid. If the pore pressure is 0, then it's going to be behaving like a dry granular material, and it's going to have a higher friction and go much more slowly. So one way of doing this is by looking at the vertical equation of motion. So if alpha is a solid concentration, then you're going to have your hindered sedimentation and diffusion. And then you can look at what the steady state of this is and what the effective pore pressure should be, and you can convert this. So the key thing really is the Peclet number. So it's what the diffusive force is, how much shear is generating granular temperature relative to the sedimentation of the particles. So in here, and this is what will set the final shape of the distribution. And then a good thing to track, and this was discussed a little bit with gravity currents yesterday, was how do you measure the height of something? Well, the center of mass is a very good way. So the height of something, if you take twice the center of mass, it's a very good way to measure something, because the center of mass corresponds to the energy, the potential energy of this material, and that should be conserved. So if you're going to a shock capturing method, you want to start off with quantities which are conserved. So defining the center of mass as your extra variable that can track this vertical redistribution of material is a good idea. And you end up with an equation like this. This is before we look at the shallow water type part of it, where the center of mass is relaxing towards some value. There's some high order terms, but the value it's relaxing to is set by the Peclet number. If the Peclet number is very low, the center of mass is going to go to half the height. Everything is going to be evenly distributed. If the Peclet number is larger, you're going to get all the solids at the bottom and the fluid at the top, and then this Peclet number will depend on other flow properties. So this gives you the shallow water model. So you've got your normal conservation of water mass, conservation of solid mass, momentum, but then you have another equation which tracks the center of mass motion. So you can get these two-layer structures, and this center of mass, this affects the mass transport of the particles, because at the top of the flow it's moving faster than at the bottom of the flow. So if the particles are higher, they're going to be moving with a different mean velocity than if they're lower. So you can get all sorts of nice effects by putting in these extra type of equations into shallow water framework. You can get these two-layer models, but they come from understanding the basics of the two-phase flow. Now, one reason why you might want to get these models right and really understand what the friction are is if you want to start looking at Mars and figuring out what you're seeing there. So these are gullies on the wall of a crater in Mars. And you see a nice gully here. This is a picture taken from the high-rise imager on the Mars Reconnaissance Orbiter. It's got a resolution of better than 0.5 meter. So this is a couple of meters across. So it's amazing resolution. And you could imagine that, a rock has rolled down here, except there's nothing at the bottom. It just kind of stops. So if there was water, you could say, water's gone down and disappeared into the ground. But the conditions are such, you're below the triple point, liquid water can't really exist, and there's also no source of it. Maybe if it's extremely briny, but where would it come from? So where do these things occur? You also get lots of gullies on crater dunes. This white stuff here, which is part of a clue, is solid carbon dioxide. So in the winter on Mars, half the atmosphere freezes out, and in places you can get 1 meter or 2 of carbon dioxide ice sheet and also snow. So you can get powder avalanches on Mars that are made of carbon dioxide snow. And in fact, we've got pictures of nearly 100 now, I think. So that means that there must be millions of these avalanches going off on Mars all the time. So that would also be a hazard if we do ever have to live there, to watch out for. I won't talk about, but interestingly, if we take the powder snow models that we have on Earth and we put them on Mars, we get ridiculous numbers. So there's some missing physics there again. Situation becomes extremely non-Boosanesque because the density of the atmosphere on Mars is so low, so you're then talking about density ratios of 1,000 to 1. So rather than the more normal, a few percent, or at least for an avalanche, maybe 5 to 10. So they're highly non-Boostonesque, so that affects our models. Anyway, here we see hundreds of these beautiful little gullies. By taking pictures at different spots, we can build up DTMs, so we know exactly what the angle of these slopes are. So we know, if the angle's 30 degrees or more, they could be dry grain flows. But you can't get dry granular flows at angles of less than 30 degrees. If they start on something steeper, they can run out further. But otherwise, if it's less than that, something else has got to be going on. There's even a few pictures of these very strange gullies with these zigzags. But again, they terminate with little pits, but with pits with nothing in them. And these zigzags are presumably some sort of instability, but this is not something we understand yet. These black spots here, sometimes they can even look like spiders, and these are caused by the sun coming through the ice sheet of CO2, heating it up underneath, and it cracks, and then you get a plume of dust that breaks through and then settles back on top of the CO2 ice. So that's another interesting multi-phase phenomena there, which has been computer modeled, but I'm not sure how accurate that is. But often the slopes that these gullies are on, they're 7 to 10 degrees, so they're definitely much too low for any dry granular flows. People have argued a lot that they're evidence for water, but there's no possible source of this water, and any water would rapidly evaporate. So one possibility for some of them is they could be CO2 supported debris flows. So rather than having a debris flow that's supported by water, you have a poor pressure of CO2. This is going to escape rapidly, but if there's a source of that, they could keep going. Brine, if you put enough salt in the water, it could stay liquid, but again, you've got to argue where it comes from. And then there's also this possibility of these things could be caused by solid CO2 blocks. So I'm going to talk a bit about these two possibilities. So here you've got some more gullies, and you've got clearer pits at the bottom. So this idea came from Candy Hansen. So her idea was that you basically have a cornice of ice at the top. This is a southern facing slope. It's north off to the other side. So on the northern slopes you get these massive temperature differences, 100, 150 Kelvin. So this could be kind of, like a balmy 0 degrees centigrade over here, and it could be minus 150 over there. So if you had a block of CO2 ice that broke off, is it possible that somehow it could move down this slope, make this gully, then disappear at the bottom? And in the middle of one of these, there is actually a block of something still stuck there. Now there are other sorts of gullies, and these are three over here, and the reason we're studying these particular three is they were there one year and they weren't there the next year. So that's something else that we've learned a lot about Mars in the last decade or so. Before, you looked at features, particularly dunes and other things, and you didn't know if they happened a billion years ago or if they happened last year. And now we know that some of these things do seem to be static, but an awful lot of them are moving. So the surface is much, much more active than we thought. So we looked at these three particular gullies in detail, and you can see that there's the changes in these pictures between the top and the bottom. So these gullies are built up over many years, but each year they're changing a bit and developing. So we ran 3D shallow water simulations just with a very basic model, and the idea here was that we don't actually know, initially at least we didn't think we knew what the physics was. So what we were going to do is just run the models, and you've got a couple of parameters. You've basically got your normal friction, you've got some velocity squared drag term, and we're just going to see what range of parameters will fit this model. So they're not going to be physical, but we've just got conservation of mass and momentum. So we have really three parameters to play with: what the initial release volume or depth is, what the friction is, and what this velocity squared drag term is, and then we'll see what kind of actual flowing materials that might map onto. So let's just skip through those a bit more quickly. But here, for example, so we've got 4 different release depths. Along the bottom axis we've got friction, along the vertical axis we've got the velocity squared drag term, and the color tells us how far in error our simulations are. So here we're totally wrong, and it's these blue areas where we can get a match up between the simulation. What you notice is they're all very low friction, below 0.3. So this is well below what you could get from dry granular flow. So we know from this analysis that it's impossible that these are dry granular flows. They have to be supported somehow. And for these particular ones, that's these different gullies. Some of these are even harder to fit with this type of model. This shows you what the simulated flow depths are in the deposits. Let's just go across that. So the idea that we have is that there's some amount of CO2 frost inside the sediment. Now normally heat conduction is quite slow, but if something starts moving where it's steeper, then you get mixing, and the top layer can be very warm if it's in the sun, and whereas lower down it can be very cold. But if you get mixing between these things, then this CO2 is going to sublimate. So if you have some amount of CO2 that's being entrained, so as it's moving down you're picking up a small fraction of CO2 from the material below, then you get this expansion factor. So this is the density of CO2 ice, and this is the density of the gas. And this is one thing that's very different on Earth and Mars, because the atmosphere is 100 times less dense. So this expansion factor is 10 to the 5. So if you have a 1% by volume of solid CO2, it's going to produce this massive amount of gas. So you only need tiny amounts of frost to produce a huge amount of gas, which then has to move up through the column of granular material, generating a pore pressure. So if you used Darcy's law, you'd get a pore pressure like this, where you've got the permeability and so on, and you need this pore pressure to balance the weight of the material if it's going to suspend it. So it turns out that the volume fraction, the amount of frost that you need in the material, is only about 0.2%. So you need a tiny amount of frost, which most likely there's much more of this frost, since the whole atmosphere is basically CO2 and freezing. So this seems like a very likely explanation of what's going on with these gullies. And then you also have to consider how long it takes this gas to escape, and the time scale is quite long. So certainly long enough for the flow to move over fresh material, entrain more CO2 and keep itself suspended. And another interesting feature, of course, of this mechanism is that you might think, oh well, can deeper flows still be suspended? But the pore pressure is proportional to the depth of the material, because you've got a certain volume that has to escape. So if you've got twice as much material that weighs twice as much, the pore pressure is automatically twice as much. So you have no problem suspending even very deep flows. Doesn't make any difference how deep the flow is, whether it's going to be suspended on this pore pressure long enough to move. So there's a whole lot of numbers which all kind of disappear into a few non-dimensional groups. This method, this mechanism isn't going to work on Earth though, because the density of the air is too large, so the expansion factor is 100 times smaller. So to get a CO2 debris flow on Earth, you'd have to do it in a reduced volume chamber, or you'd have to put huge amounts of dry ice into your granular material. So I'm still trying to sort of figure out if there's some way to do something similar experimentally to see if this process can happen. The other types of gullies that I showed though, we think there are these blocks of solid CO2 which are sliding down. And here, if we just imagine the static situation, first of all, we have some block of CO2 ice sitting on some warm sand. So there's a heat flux into the ice. It's subliming here on the lower surface, and this CO2 is being forced through this porous material. If we can solve these equations, we can figure out what the pressure is under this block, and you can imagine this as a long rectangular block or a circular disk for mathematical purposes. See if there's much difference between them, and see when is it going to levitate. And this is a bit like the Leidenfrost effect, except it's with sublimation rather than boiling, and see what the difference would be between Earth and Mars as to the effect of this type of thing. So I'm not going to go through the equations for this now, but you can solve all of these things very nicely analytically, both in 2D and 3D, so you can show what's going to happen. And we actually went out into the desert in the north of Arizona and Utah. So this is black basaltic sand, which is as close as you can get to Mars. Now, black sand in the summer gets very, very hot. This got up to 85 degrees centigrade, the sand temperature. And it actually melted the soles of my shoes. The glue came off, so I lost the soles of my hiking boots doing these experiments. These are for calibrating the camera, so we can calibrate the speed. We've got a LiDAR, so we can measure the surface slope properties very quickly and look at the surface evolution. And this is Candy Hansen. First of all, just to show you, even though this is quite a steep dune slope, this is a block of water ice, and it's just not going to move at all. It's going to melt slowly. Some of the water's just going to disappear off into the sand, and there's nothing much going on. Now, Candy is an awesome planetary scientist, and she first wanted to do this. Her Mother's Day present was to get her children to go out into the desert with her and carry CO2 blocks and do a proof of concept. This is a block of wood which is not moving down either, and you won't get any sand avalanches. This is about 20 degrees, so this slope is completely stable, whereas here, even on a gentle slope, if you do it with a block of CO2, it's subliming at the bottom, and even if the pressure's not enough for it to completely suspend itself, levitate, it will reduce the friction in proportion to the total pore pressure to the weight, and it just carries on going. Even on this gentle slope. No, this is actually a much gentler slope. So you can actually you can put an Explorer on top, and I filmed this from a dune buggy, so the park rangers were very happy to help us with this. They love driving around in the dune buggies, and it's quite fun. So you can go along, and you can see how gentle the slope is, and then this also gives you a good insight into actually what is the dominant frictional effect. And it's basically ploughing. So it's the surface roughness height times the velocity squared is what's setting the drag of these things and causing the erosion. Now, what you might not know about dry ice is you can drill into it pretty well. So we put a GoPro on the top of this one. So you can see it's a pretty turbulent ride. It's hitting any lumps in the surface, which is slowing it down. But here it's getting onto something much more gentle and smooth, but it just carries on because it will levitate for a long time till the sand underneath it is cooled down. So it will essentially move on any slope, and now it accelerates again. So we're now trying to create a proper model for the full erosion, so we can look at this at Mars. And I didn't go through all of the maths here, but what's amazing is that the mobility of these things on Earth and Mars is essentially the same, when they should levitate and when they should move. So that's what's nice, and we've checked this out now on Mars pretty well. Now if you get repeated, this is on a steeper slope, if you do this over and over again, you can see it's starting to form a kind of a washboard pattern, so the surface is becoming unstable, and this then actually reduces the speed of these things because they've got larger lumps to hit into. The roughness scale is increased, and what happens is, if it starts off smooth, it builds up some natural roughness scale which will set the speed and the erosion rate. If it starts off rougher because of the wind, then this roughness will decrease till it gets to this equilibrium point. So we've got a model now how that works. And then I said before, you get these pits at the bottom. So if the block stops at the bottom, if you put a block of CO2 on some ballatini, it will actually sink down through this and then bubble away underneath. Then if you leave this till the CO2 goes, it can take, depending on the size of the block, it can take a few hours. You end up with a big pit because it's just chucked all of this stuff out. Now, I wanted to do this in a Mars chamber as well, and you think, okay, it's all going to be the same, Darcy's law, same size particles. But of course, because the pressure is so much lower, the heat transport's all the same, but the velocities are much, much higher, 100 times higher because of the expansion factor. So when we put this into the Mars chamber at OU, the whole thing basically just exploded, and there was like small ballatini everywhere. So there is something different. You need to then, I think in Mars it's more of a Forkheimer thing because the velocities are much larger. So there's a big difference there from the pressure. The other effects are similar. And really all that happens here, what's important at the end of the day is the aspect ratio of the block, and the rest of it is set by a time scale, which is basically about 3 seconds on Earth and about 4 seconds on Mars. So it has to move over fresh material in this time to keep suspended if the aspect ratio is, you know, a tenth or something like that. I'm going to skip through this. The reason I put this in is this is work with Eckert, but it's also related to what Colin was saying about the stability of these types of flows and the history of them. So these are steady state. This is a steady state gravity current. So we're doing some funny forcing at the bottom. If we wait a long time, we can get the gravity current to become stable, and it becomes unstable at the head and basically stable at the back. Because if you run this from the beginning, the whole thing is unstable, and it takes a long time to reach this state. So this is related to what Colin was saying about the history dependence of these flows. And they actually can be stable at quite high Reynolds numbers further back. But by studying these stationary flows, you can actually get good statistics. So there's always been controversy about the models for what the front conditions should be at the head of these type of currents. So this is what it sort of looks like close up. So you can look at all the momentum balances, and the pressure drops, all of this type of stuff. And I think with these type of stationary simulations, because you can do them as long as you want, you can get good statistics, you can answer some of these questions. And hopefully this will be published soon. And what you see in the reason these things become stable, so if we look at the profiles at the front, you know, we get the step profile here. Further back, the density profile is diffused out. But this is also what happens though with the velocity and why it becomes stable at the back. So towards the front we have this big change in velocity, which gives rise to Kelvin-Helmholtz instability. But further back, the velocity is completely smoothed out. So we don't have, the Richardson number is too high, so the thing becomes stable. But it takes a long time for this to happen, and that's why the history is important. So for a normal experimental lock release, this isn't going to happen. The current's not going to go long enough to do this. But this may be the reason that this may be another reason that turbidity currents in the ocean can last so long, though, is that they develop these much more gentle velocity profiles, which are no longer unstable, so that they're not entraining the fluid anymore and the ambient fluid and being stopped. And yeah, let me go through some of that. Just how to avoid avalanches. Don't do this. This is Slab Avalanche. First of all, don't ski down 3 people at a time. Send one person down who doesn't have children first. So these are the most dangerous avalanches. These are for skiers. These are slab avalanches. So what you saw here is they've gone into the middle of it and then it fractures with them all around, and this is caused by the wind depositing the snow on lee slopes, and it has been pretty windy round here, so there's a lot of slab about at the moment. This one's about 2 meters, and you get out into the middle and it will fracture underneath. No, not all of them. Then there are other hazards with doing experiments with snow, but these can be mitigated by the use of PhD students. So you send them up when the gate doesn't release and the snow doesn't come down. You can send them up to get things going. There's intentionally no sound here to protect those who understand German swearing from. I don't have to have a warning. So first of all, you have to. So it's quite hard work doing experiments with snow. 'Cause cohesive materials are a nuisance. And just to finish off, what we've got now is with our latest instrumentation that we have in Switzerland, we've got this really nice radar system. So we can look at very high frequency, 100 hertz or so, every 75 centimeters at the avalanche coming down. This is a space-time plot. So this is the front of, this stuff is noise, but this is the front of the avalanche coming down, and the velocity is gradually decreasing, and you can see the tail, and the avalanche is getting thinner. So at this point, this is a sort of a schematic. The avalanche is 100 meters long, and then it's slowly slowing down from the bottom, coming to a point, and it's pretty homogeneous. So this is a small avalanche, and it's gradually stopping from the back. So these are the type of things that the models have to get right, which they won't at the moment. And what we've seen is there's other type of stopping mechanisms. So here the avalanche front's coming down, there's a tiny bit continues, but mostly it stops, and then there's a backward propagating shock. So it's deposited, and the snow's bashing into it, so there's a kinematic wave moving back up the slope. So this you can see easily with experiments, but again it's tricky to get all of these different stopping mechanisms. Now if you've picked up warmer snow into the avalanche and it's cohesive, and the whole thing moves much more like a solid block, and the fact you see these lines on the surface here, that means that it's really a pseudo plug, and the surface has got these waves or undulations on the top which are frozen, so it's just moving down. So this is due to the temperature that's been picked up into it, so it's just sliding along and then it stops suddenly. So as well as the type of shallow water model I showed earlier, you need to also look at the temperature of the snow and the temperature of the snow that's entrained if you want to get this transition between dry snow and dry non-cohesive snow and cohesive snow. And then you can also just get fading where the avalanche just gradually dissipates, and this is if it just deposits from the bottom. So this is the traditional model that's incorporated, but so this is what current theories will do, but they won't produce any of the other mechanisms which occur most of the time. So we can classify them into all these different sorts of shapes. Here you can see all sorts of avalanches all happening at the same time. I won't go into more details. The interesting thing here is high up on the mountain, it's moving very, very fast. We've got the dry snow coming down. The dry snow is going all the way down really quickly, but it's picked up a whole lot of wet snow, which then goes along much, much more slowly. So there's this complication that maybe you even need more than one layer in the dense part to deal with this. And this could happen in general with all sorts of geophysical flows. If you're eroding different sorts of material than it's initially flowing, then you're going to get different dynamics from it. Let's stop there. So thanks very much.
Thanks.
You just before you ask questions, this is not just a pointer. But no, please ask questions.
Just a question about the Mars stuff. Obviously, one of the hardest things is to estimate what the initial volume is that's released. One of the how do you do that in practical terms?
Well, we just tried lots of different volumes and saw which ones would then match up. So the problem is your depth resolution. You can do these before and after DTMs, but you're only talking about half a meter of material, or even maybe at most a couple of meters, and that's barely resolvable with the DTM, so you don't know for sure. You have to try different things, so that is unsatisfactory. Whereas, if we're doing experiments on Earth, you can do very accurate laser scans before, so you can measure to within a few millimeters, so you can know exactly the release volumes. But we can't do that on Mars. But maybe if we put a better camera up there.
We need astronauts.
Yeah. You probably don't want to send them up onto these slopes, but.
So thank you very much. Incredibly interesting. So I missed probably why you don't find the rock at the end of Mars.
Because they're CO2 blocks. So the CO2 blocks slide down, and then they disappear, they
Second-
sublimate.
Okay, second question is why your avalanche that you had an infrared image of
Yeah.
it is actually so different in temperature. So is it with the ground that you have a heat flow?
Exactly. So normally, if you're high in the mountains and it's permafrost, it will be colder, but mostly the bottom of the snow is at 0 degrees. And then on this day, it was very cold outside, so it's about -15 on the top. And there's a roughly speaking, linear type of temperature profile. So the cold snow is on the top, and if you see where it's eroded down to, you'll see that from the temperature. So it's picking up this warmer snow. So, the snow grains have to fall a couple of 100 meters to rise 1 degree from the dissipation energy. So that's very small compared to the gradients. So the thermal cameras are fantastic for enabling us to calculate erosion depths and things like that.
Very nice talk. So what's the most important difference between real avalanches and this Bruce Ness type of gravity current simulations in your experience, like top 1, 2, 3?
The biggest difference is to do with the snow that's entrained and the temperature of the snow. That's huge. So that will change the avalanche speeds from 30 meters a second to 3 meters a second. So that's the most important thing. And then the second thing is we don't have a good model for this transition of the dense flow and the mass exchange between the dense flow and the powder cloud going both ways. So I think there's very little momentum coupling between the two. That's not important. The powder cloud momentum exchange is all with the air, but what the mass exchanges between them is the second most important. Andy.
Yeah, it was very nice talk. Thank you. I was wondering, going back to your first point about trying to avoid avalanches, that the initial conditions are going to be very important, both
Yeah.
of the, what actually fails on the slope, but also the subsequent snow it flows over.
Yeah.
So how would you go about characterizing the initial conditions to generate hazard maps using these models?
Okay.
What is it you'd want to go and measure?
Well, okay, so for generating hazard maps, all the good ones are done with the historical record. The models are not good enough to do that. But then for the initial conditions, you do snowpack evolution models. So you do a 1D sample through the snow and you solve the heat flow, water vapor transport, and then you have equations that you quantify the snow crystals by their dendricity, their size. You evolve all of these things, and then you put weather information in as a top boundary condition. And that's one of the things that's very hard to get right with the slab formation is the local weather depends very closely if you're near a ridge and you have flow separation and things. But what we did when we're trying to match up these avalanche data that we have with the dry and the wet snow is we run the snowpack evolution models at all points on the slope, so we think we know what the snowpack is, and then try to match that up with what we observe. So they don't really use the models though yet for assessing the risk. They're not very good. But what you'd say basically is like how much, if you're looking on a kind of a yearly basis, it's like how much snowfall do you get somewhere and what the slope is all to do with the slope angles and the aspect ratio. If they're northerly, then the evolution of the snow crystals is very slow. So they take a long time to stabilize. If it's a south-facing slope, then the evolution is much quicker, so they stabilize much faster. So this time of year, don't ski any steep north-facing slopes unless someone else has gone first. And you can dig snowpacks to try to figure out all the layers, but in terms of avalanche safety, the sort of training has really moved away from that, and it's mostly focused now on group dynamics. So it's like groups of men with one woman are the most dangerous. So guys will show off, but it's a question of communicating so you don't all ski down at the same time and properly having the same objectives. It's much more important really than looking at trying to find a weak layer, because you're very likely to miss that.
Any other question? I do have one. Is there any use for like the kind of the mu-I rheology for these type of models, or it really never works because it's never in the right conditions?
Well, so the mu-I rheology is ill-posed, so that's a problem with why you might not want to use it anyway. But once you come to depth averaging, all that you really care about is the friction on the bottom surface. So there's the earlier work by Pouliken where you and in fact to actually get H stop, you don't really get that properly from the mu-I anyway, where you're basically just setting your bottom friction as a function of the flow depth and flow velocity. So that's the right type of thing for the dry avalanches. But it's problematic if you're trying to do a shallow water expansion to find out, because what you also get is when small avalanches don't form roll waves, they stay smooth and homogeneous. But larger dry avalanches, they do form these roll waves. So what you'd like to do is develop more sophisticated shallow water equations which would predict this transition. But you can't do that with the mu-I rheology because it's ill-posed. So we need a better granular rheology that doesn't have this problem, and then we might be able to match up when we get roll waves and when we don't.
So you showed this very nice movie on this solid CO2 sliding down.
Yeah.
So I assume that friction to this is provided by air friction of this object, but I wonder whether the angle from which on it will slide down is understood.
Well, if it's completely if it's completely suspended, if the integrated pore pressure equals the weight of the block, then it will slide on any angle because it's like an air hockey table. If it's partly suspended, then there's a fraction of the pore pressure to the weight, so then that will tell you what angle it will slide at. But we've not quantified that because we couldn't make dunes of all the sizes that we want. But that would be something that we will try to do in the lab in the future.
Maybe a final question about the modeling. You mentioned something with the boundary condition. You do not impose any boundary condition for the mass flux at the slope, or in your shallow model usually.
Oh, yes, yeah. So we did have an erosion there, and that's also something that's very poorly understood. Is what does the erosion rate depend on? Is it depending on the normal force, the shear stress, the turbulent energy inside the flow? Generally with the avalanches, it seems like they erode pretty quickly, and there's a certain amount of snow that's erodable which will just be eroded, but that's not a very satisfactory model. And part of the problem there is it's very difficult to do laboratory experiments on erosion. You want a granular flow that's flowing, and then it's difficult to have that moving over something static that's going to erode and not flow as well. But the best thing there would be some really good experiments. People could devise a good setup so that could be properly quantified and understood. But that's also a big, actually, so someone asked what are the three unknowns. I'd say that's the third biggest unknown is how to parameterize or understand these entrainment mechanisms on the basal surface, and this holds for landslides and rock slides and debris flows as well.
All right, thank you very much.